Welcome to the explainer. You know that feeling, right? You're staring at a long list of numbers you need to add up. It's tedious, it's boring, and you just know there's a better way. Well, today, we're not just learning math, we're building a problem solver's toolkit, one that turns those painful calculations into quick, elegant solutions. Okay, let's just dive right in with a challenge. You could, grab a piece of paper and start grinding it out. 2 plus 4 is 6, plus 6 is 12, plus 8 is 20, but you can already feel how slow that is. And worse, one little mistake and the whole thing's ruined. There has to be a better way, doesn't there?
Oh, you bet there is. And thankfully for all of us, some brilliant minds have already done the heavy lifting. They've given us a set of incredibly powerful, super reliable tools to solve problems just like this. Not in minutes, but literally in a matter of seconds.
But, like with any tool, before we can use it, we have to know what it's for. So, our very first step is to learn to speak the language of progressions, and that means getting one crucial distinction absolutely right. Okay, so here's the deal. A sequence is just the list of numbers itself, the ones following a pattern, like 2, 5, 8, where you're adding 3 each time. A series, on the other hand, is what you get when you actually add all those numbers up. So a sequence is the list, a series is the total. Simple as that. And this is a brilliant way to think about it. Each number in the sequence is a single step you take. The series, that's the total distance you've traveled after taking all those steps. It's a simple little analogy, but it's one that really sticks. All right, let's grab our next tool. And this is the real magic trick. This is what lets us skip all that boring grunt work of adding numbers one by one. Now, what's really cool here is how we can kind of discover the formula for ourselves. So let's take a simple series, 2 plus 5 plus 8 plus 11 plus 14. Now, right underneath it, just write it again, but backward. And here's where the magic happens. Add the numbers vertically, column by column. Something amazing happens. Every single pair, 2 and 14, 5 and 11, 8 and 8, they all add up to the exact same number, 16. So that clever little pairing trick we just did, it leads us directly to this beautifully simple formula. The sum, S of n, is just the number of terms n divided by 2, all multiplied by the very first term a plus the very last term l. That's it. So elegant.
Right, this is a fantastic question because it's a super common problem. Maybe you know where a sequence starts and you know how many steps you're going to take, but you have no idea where you'll end up. Well, no problem. Our toolkit has another tool for that exact situation. And here it is, our second summing tool. Now, I know it looks a little more complicated, but all it really does is swap out that last term L for something we often do know, the common difference D, which is just the number we're adding each time. Okay, let's put this thing to the test. Our first term A is 3. The difference D is clearly 4, and we want the sum of the first 20 terms, so n is 20. See? We have every single piece of information this formula needs.
We plug in the numbers, do the quick math, and bam, 820. Just take a second to appreciate that. We just found the sum of 20 different numbers in one clean calculation. That's the power of having the right tool for the job. So finding sums is now officially in our toolkit. But what if the problem isn't about the total, but about figuring out a specific spot along the way? What if there are gaps in our puzzle? This is a classic, almost like a detective story. We're given 2 clues from somewhere in the middle of a sequence, and we have to work backward to figure out where it all began. And a challenge like this, it calls for a new and very powerful tool. And here it is. Folks, this formula is the master key of our entire toolkit. It lets us find the value of any term, t of n, at any position in a sequence, as long as we know the first term a and the common difference d. This little guy is the foundation for solving almost everything else. So, using our new master key, we can translate our 2 clues into 2 neat equations. For the 5th term, n is 5, which gives us a plus 4d equals 20. For the 12th term, n is 12, so we get a plus 11d equals 48. And just like that, we have a system we can actually solve. So, here's the crucial part. By solving these 2 equations together, we find our missing pieces. The first term, a, is 4, and the common difference, d, is also 4. We've just reconstructed the entire secret code of the sequence from just 2 little clues. Okay, so we've built a pretty complete toolkit for finding sums and for finding any term we want. Now let's take these tools out of the workshop and see how they solve problems you might actually run into in the real world. Now, at first glance, this just looks like a question about money, right? But with our new toolkit, we can see its hidden structure. This is a perfectly disguised arithmetic progression problem. That starting salary is our A, and that monthly raise, that's our common difference, D. We need to find the salary in the 12th month, which is really just the 12th term. So we pull out our master key, the general term formula. We identify that A is 1,000, D is 50, N is 12, and we just plug them right in. It's a direct, simple application of the tool we just learned. The calculation gives us $1,550. And this isn't just some number in a math problem. This shows how these tools have real power for practical things, like figuring out your future income or planning a budget. Before we wrap this up, a quick pro tip. Here are the most common traps people fall into. Seriously, always double-check N, the number of terms. Never mix up D, the difference, with L, the last term. And the biggest one of all, always remember it's N-1 times D. Do not forget that -1. So, the key takeaway today is that you are now equipped with a powerful and really versatile mathematical toolkit. You've got the formulas, you understand the logic behind them, and now you can approach any standard arithmetic progression problem with confidence and, more importantly, with speed. Everything we've talked about today involves lists that have a clear ending. But I want to leave you with a question. What happens if they don't? What if a series just keeps going forever? Could you actually add up an infinite number of things and still get a single finite answer? Well, that's a puzzle for another time, and it's where mathematics gets really, really interesting.